welcome to the Advanced Power Electronics class, and happy 2015 and happy new semester. I don't know if you have been here before or not, or this is your first semester. Raleigh is usually not as warm as it is this year. So what I'm going to do today is I'm going to go through the course syllabus and the schedule, and then start the material basically. If you are a distance student or if you're an on-campus student, I try to merge these two sections together on Blackboard. Hopefully, by this afternoon, you are going to see some sort of an advanced power electronics in your Blackboard. And if you click on it, there's a bunch of information. I usually only post the stuff under content. So if you click on content, there's a course syllabus and there's a course schedule. Looking at course syllabus, kind of an introduction of a class, and by the way, a lot of times students toward the end of the semesters are asking me questions, and those questions are already answered in the syllabus from the beginning of the class. So please take a look at it to figure out how, for instance, I do the grading and things like that. So let's go through it very quickly. I don't know what is going on here. This computer is, okay, very, very slow. Okay, so the number of the course used to be 453, EE 453, and they did the renumbering, and now it is 6520. Apparently, all of the power classes, the second digit is a 5, and because this is a graduate level class, it starts with a 6. It's a 3-credit-hour class. We meet here on Tuesdays and Thursdays from 2 p.m. until 3:15. This is 262 Mihal, and if you're a distance student, you are not required, you're encouraged, but you are not required to dial in a real-time fashion. You can watch the lectures later. The description of the course is pretty much power electronics that you have had before, and hopefully you have had before, in a little bit of a more depth. We dive into, for instance, how to synthesize a power electronic converter, how to do a small signal modeling. We look into power factor correctors, things like that. As far as the instructor is concerned, it's me, Mehdi Ferdowsi. I have been with this institution since 2004. This is my 22nd semester, basically, of teaching. My office hours, I'm in 234 Emerson Electric Company Hall, E, and my office hours are on Tuesdays from 10 to 11. But anytime, if you have a question, as long as it is a short question, you are more than welcome to stop by. If it is a long question, when you stop by, ask me if I have time for a long question, for instance, the meaning of life and things like that. Short question, anytime I'm there, you're more than welcome to stop by. But other than that, you can send me an email and we can set up some time. The material that we are going to be covering, some overview material, then we look at a review of conventional power electronic converters, what you have seen before. A lot of you have already been exposed to that material. All I do is just make sure that we are all on the same page so we understand each other before we take off. We look at some Fourier analysis of power electronic converters, then a small signal modeling, then voltage mode control, then current mode control, then some soft switching techniques, and then some power factor correction approaches, and then multi-level converters and PWM techniques. So a variety of newer or more advanced topics in power electronics. How are you going to be evaluated? If you are an on-campus student, we have 5% of attendance. But I do not take attendance during the first and second weeks of the class. So starting 2 weeks from today, I'm going to bring a sheet over here and you have to sign your name. Please make sure that this is your responsibility if you're late to the class to find that sheet and sign it. If you're late and I don't know who's going to sign and who's not going to sign. So please make sure that you sign it unless we have a quiz. If you have a quiz that day, we don't need attendance because by not attending, you're going to lose the score of the quiz anyway. Then 47.5% of homework assignments, then 47.5% of quizzes, and I'm going to show you the schedule of our quizzes. If you're a distance student, obviously attendance doesn't make sense, so 50% quiz and 50% homework assignments. The way I map your score of from 0 to 100 to A, B, and C is like over here. From 90 to 100, you get an A. And from 80 to 90, you will get a B. And please note that 89.99 is still a B, even though it's very close to the threshold, but it is still a B. And unfortunately, I can't do anything about it. If I remember correctly, like last time that I taught this class, which was the fall of 2012, I believe, I would say almost everybody got an A. We had a few students who got a B, basically. I wouldn't say it's an easy class, but everybody was very, very enthusiastic about the topic. By the way, this class, as a graduate level class, is only offered once every 2 years. So, for instance, the next time that this class is going to be offered is going to be the spring of 2017. Hopefully by then you're all out of here. Homework assignments. I will not accept late homework assignments. If you are, again, for every homework assignment, I mentioned if this is if electronic submission is required or accepted, or you have to turn it in class, basically. So each homework assignment may be different, and I won't take late homework assignments for any reason that you couldn't submit it, then you just missed that point. You are encouraged to work together. Sometimes there are computer simulations that you may actually talk to your friend, how did you do it? But please do not just copy someone else's simulation file, because I can easily find out if this is an original file. Looking at some MATLAB tricks, I can easily find from who this file was originated. And please make sure if it is a MATLAB simulation file, it's a blank file that you start with and it is originated by you. Otherwise, I may find out. We are going to have 6 quizzes during the time of the class. I'm not going to do any makeup quizzes. For any reason, if you miss a quiz, you have missed a quiz. Excuses that I've heard before. I was sick, my dog was sick, my cat was sick. I don't know, it was snowing and they didn't plow my street. I broke my arm. My cousin was getting married in California. I'm the best man. I mean, things like that. I don't care. If you are not here and if you're not going to take the quiz, you're just going to lose the score of the quiz. However, there's a compensation mechanism. At the end of the semester, this is the compensation mechanism. There will be a final exam. The score from this exam will be used to replace the 2 lowest quiz scores if it is beneficial to you. So for any reason that may or may not make sense, if you miss a quiz, your chance to compensate for that would be taking the final exam, basically. However, if you do really well in all of the quizzes, you don't basically need to take the final exam. All right, so this is about the quizzes. Attendance, this is for on-campus students only. And 5 points out of 100 is for attendance. And if you miss up to 4 classes, that's fine. We are all human. Sometimes we get sick. Sometimes we are not in the mood. And beyond 4 absentees, basically, I'm going to start reducing from that 5%. There are a bunch of links over here. They are kind of classic stuff. They appear on a lot of, the syllabus, so you can take a look. For instance, the academic dishonesty procedures and rules and exit procedure for the classroom. There's only one entrance door. There's no way you can miss that. Disability support services. If you are having some sort of a disability, take a look. You may actually get extra time, for instance, for your quizzes. A bunch of references for the class. I do not use a particular textbook. I use my notes, but you're more than welcome to spend some money and buy one of these books. If you want to buy one, they are all very good books, by the way. Power electronics, it doesn't vary from one book to the other. They are pretty much covering classic stuff. But the one that my notes are closer to, not identical, but closer to, is number 4, Fundamentals of Power Electronics. And there are 2 links over here that they provide some of the slides that the authors of the book have provided, and they are free. You can actually download them. You just click on the link and it opens up chapter 1, chapter 2. It's a very good book. It's a very math-oriented book. And some of my lectures are very close to the material that is provided in this book. Some of them are not. I just provided a long list of books over here, and as I said, they are all very good books. And in the end, I have a bunch of links over here. I call them useful links, like PELS, Power Electronics Society of the IEEE. One of the links is there if you want to become a member. PSMA, Power Supply Manufacturing Association. They have some white papers sometimes. There are job openings, for instance, sometimes they'll list. You can take a look at some of these links. And some of them are like newsletters, like PowerPulse.net number 8. You can subscribe to it, and every day or every week they send you highlights of power electronics, what is going on in the world of power electronics, basically. And the last one, number 12, I haven't checked it recently, but if I remember correctly, it was a free book on power electronics. I don't really remember what the quality of the book was. It just put it here if someone wants to take a look. Any questions about the syllabus? Okay, so no questions. Let's take a look at the schedule of the class now, which is also posted here on Blackboard. Okay, so we are, first of all, I regularly update the schedule. Like the last time that this schedule was updated was the 15th of January. We are here on the 20th of January, and usually if you look at Blackboard, there's also a little bit of a note over there, when was the last time this file was updated. So we just go through this, a rough estimate of what is going to be covered and when it is going to be covered. And as I said, the first 2 weeks, these 4 sessions, I am not going to take attendance. Starting February 3rd, I'm going to bring that attendance sheet. And that is when your first homework assignment is due. It's not posted on Blackboard yet. Then after that, basically every week, every Tuesday, we either have one homework assignment due or one quiz due. So the week after that, there's a quiz, then there's a homework assignment. And you just roll down the semester all the way down here that we have quiz number 6 and then finally homework number 7. If you choose to take the final exam, it is dated for Tuesday, May 12th. And as it's a very odd time. It starts at 7:30 a.m. This is the first time that I'm noting the final exam is earlier than 8 a.m. So just keep that in mind. It's an early final exam. Any questions about the schedule? All right, so these documents are already uploaded on Blackboard. All right, so let's take a look at the content of the class. Usually in a power electronics class, the first session, you spend a little bit of time about what is power electronics, what are the applications of power electronics. I'm assuming that since this is an advanced class, you already know what power electronics is. Otherwise, you shouldn't take the class. But in any way, if you don't know, power electronics is, I would say, the art or the technique of converting one form of electricity to another. For instance, you have a computer which consumes DC power. The CPU, the central processing unit, or the motherboard of your computer, your desktop computer, consumes DC power, let's say 3 volts or 2 volts or something like that. And the power that is available at home to you is 110 volts RMS AC. So you need to convert this form of AC power into DC power to be able to, for the computer to be able to use it. So that is the power supply of your computer. Same story for your laptop. For instance, your laptop has a battery of about 20 volts. But again, the CPU consumes about 3 volts or less than 3. So again, you need to have a DC to DC converter to step down that 20 volts into less than 3 volts. Other applications, when you have a renewable, like for instance, renewable resource, for instance, a solar panel, and you are trying to tie this solar panel to the power grid, solar panels give you a voltage of about 30 volts of DC, and then the power grid is 110 volts RMS AC, so you need to have some sort of a DC to AC inverter to do the job for you. So whenever your source and load are not compatible with each other in terms of amplitude, in terms of type of the signal, is it DC or AC, or in terms of even frequency, you need to have some sort of a power electronic converter. So if you classify power electronic converters, you can classify them into DC to DC converters, like in a laptop or in a cell phone, DC to AC inverters, like the solar application, and then AC to DC rectifiers, which is the power supply of a desktop computer, and then AC to AC converters, for instance, for a motor drive. Power electronics is a relatively new topic. It was born, I guess, back in the late maybe 60s and 70s when semiconductor devices were born, and then it has grown and grown and grown to the extent that many things that were not possible many years ago due to cost issues or reliability issues or efficiency issues, they are possible now because power electronics can offer you those solutions. One thing that you may note is, for instance, the chargers for your phones, which is basically a power electronic converter, is much smaller than maybe 10 years ago. So you can see still power electronics is growing. The size of power electronic converters is basically shrinking. They're getting smaller and more efficient. And the cost is actually going down. So it's getting cheaper, more reliable, and actually less volume and less weight, and more efficient. So there's a lot of new applications for power electronics on the horizon. As I mentioned, for instance, renewable resources. When you have a bunch of solar panels or you have wind generation, you definitely need a power electronic converter. In automotive applications, for instance, electric vehicles and hybrid vehicles, you need a lot of power electronic converters to interface between the battery of the vehicle and the motor drive or the generator, and things like that. So this is a field that has been exciting for the past, I would say, 3 decades, and it is actually even more exciting now than it was maybe 10 years ago, 20 years ago. Any questions so far? So that was a kind of a brief introduction of power electronics. And as I said, we usually, most of the time in this class, we are going to focus on DC to DC converters, how they are analyzed, how they are built, how we can simulate them, how we can control them. And then we spend a little bit of time on inverters. We spend a little bit of time on rectifiers. So the majority of the class is dedicated to DC converters. All right, so to make sure, again, the material that I'm going to talk about right now is pretty much, you have seen it before. I just want to make sure we are all on the same page. If you have taken power electronics in another institution, in your home institution, or you have had maybe industrial electronics instead of power electronics, I just want to make sure we are all on the same page. I'm going to introduce or review, basically, because they have been already introduced to you, maybe 3, maybe 4 classic DC to DC converters, and then beyond that, we are going to actually cover our new material. So the classic converters that we talk about, so we're talking about DC to DC converters. Let me make this a little bit thinner. Probably this is the thinnest possible, DC to DC converters. The first one, which is the simplest one to analyze, is called the buck converter. And sometimes they call it the step-down converter because it steps down the voltage. All right, so the schematic of the system looks like this. So we have this DC source. It could be a battery. It could be a solar panel. It could be a large capacitor. It could be the output of another stage, an upstream stage. But anyway, we just call it a DC source. Then you have a switch. And later on, we talk about the switch. What is the nature of this switch? Is it a MOSFET? Is it an IGBT? And then we have a diode. So these 3 elements are in loop, and then we have another loop of an inductor. and a capacitor, and ultimately your load. So again, I'm assuming that my load is a purely resistive load. That may not be the case in some applications. It could be another converter, it could be something else, but just for the sake of simplicity, you always assume your load is a resistor, and other types of loads are considered special cases. So we have this switch over there. We usually label them as S or maybe SW, and a diode D. And obviously this is the inductor, capacitor, load, and input voltage. And the output voltage. Now be careful about this letter D, because sometimes it is the name of a diode, sometimes it's the duty cycle that we are about to introduce, and sometimes it's representing differentiation. So there are lots of these in power electronics. And this switch is, if you are curious about it now, but later we are going to talk about it, most of the time this switch is a MOSFET basically. An N-channel, okay, let me make it a little larger. All right, we are going to introduce the switches later, but again, remember, switch has two terminals, and the third terminal is basically the control, or the gate basically. So this is your gate, and then you have a source and a drain. So the gate is actually the control that is applied over here, that is commanding the switch to be on or off. All right. In power electronics, we usually assume that the elements are ideal, in a sense that if I have a switch and this switch is closed, it is like a short circuit, basically. There is no voltage drop across this switch, so it's an ideal switch. Obviously, it's in practice we don't have ideal switches, but it makes a lot of sense to assume our switches are ideal because, for instance, if your input voltage is 100 volts, and in a real switch you have about 1 volt of voltage drop, 1 volt of voltage drop on your switch compared to your input voltage, which is 100, is only 1%. So it makes it's a good approximation to assume that this switch does not exhibit any voltage across its terminals. Same story for the diodes. In microelectronics, it's all about what is the voltage drop on the diode, 0.7 volts or whatever it is. Here we assume that the diode is ideal. And then later on, if you're interested in, for instance, in conduction losses, then you have to come back and again assume that your diode is a non-ideal diode. So first you assume everything is ideal, you do all the analysis. If you are interested in losses, you come back and then assume, okay, the components are not ideal, so I have, for instance, I have to look at the RMS value of the switch or something like that. But for now, don't worry about it. Just assume all of the components are ideal. The inductor is also ideal. It's a linear inductor. It doesn't exhibit any internal resistance. The capacitor doesn't either, and therefore everything is ideal. So my switch is an ideal switch, meaning that when it is on, it's like a short circuit, it's like a piece of wire, and then when it is off, it is like open circuit basically. It doesn't matter how much voltage appears, and there won't be any conduction in the switch. The diode is also the same. There is one input to the system. The input is the command that you are applying to your switch, basically this command over here. All right. So the input to the system is this signal, which is coming from your controller, and later on in this class we are going to see how we can design a controller. But anyway, the command is going to look like this. Command for us, the switch. Okay, so first of all, the command is a periodic signal, okay, with a period of T, capital T, which is 1 over F, the switching frequency. And then in this periodic signal, we have two states. We usually start with the on state, and then we hold on to that state for a period of time, which lasts for the duty cycle times period. And then for the remaining portion of the period, we just turn the switch off. So switch is on. So if time is between all right, so something like this. So each period is divided into two segments, and this is a definition for the duty cycle that I'm using lowercase d to highlight that. So d, which is the duty cycle, so D highlights the ratio between the on time of the switch to the period, the switching period. So if my duty cycle is 0.5 or 50%, that means for the first 50% for the first half of the period, the switch is on, and then for the remaining half of the period, the switch is off. If the duty cycle is 0.75 or 75%, that means the switch is on for 75% of the period, then it is off for the remaining 25%. So remember, the duty cycle is a number without any dimensions that is between 0 and 1. All right. The other assumption that we make when we are analyzing this converter is we are assuming that we are going to simulate converters later. When you start a converter, you go through a transition, and then you reach the steady state. We always do, or most of the times, do the analysis for the steady state conditions. So the analysis is made for steady state conditions. Or we just call it SS. So a steady state means that all of the signals have settled around a steady average value, and they are on average neither rising or falling. On average, they are almost constant, or actually are constant. Or if you look at, for instance, the inductor current waveform or the voltage across the capacitor, they are periodic waveforms, but the initial value of the signal at the beginning of the period equals the final value of the signal at the end of the period. So steady state means the implication is on average, okay. On average, okay, again, the symbol that I use to take an average of a signal, highlight the average of a signal is something like this. So this means average. So on average, the inductor current is constant. Okay, this is IL. So on average, the inductor current is neither rising or falling. It's almost constant. It is constant. Also, on average, the capacitor voltage is constant. All right, the capacitor voltage is the same as the output voltage, basically. All right. The other assumption that we make is this capacitor is large. And later on, we are going to see what we mean by large. But the implication is this capacitor is large enough so that the output voltage is almost a DC signal. So we are talking about a DC-DC converter. Therefore, it makes sense to assume that the output capacitor is large enough to hold a DC signal, DC voltage, and then later on we have to find an equation that guarantees that that assumption is a valid assumption. So one other assumption is C is very large. C is large, therefore VC is almost constant. Like a DC signal of VC. All right. So again, in this class, if a signal is DC, we use capital letters to show them. Like here, capital V sub C is the DC component or portion of the capacitor voltage. If we don't know what it is, we use lowercase, which could be AC or DC or combination. So we make all these assumptions. Now let's take a look at the voltage transfer ratio of this converter, okay? So we have two modes of operation. Mode 1. And then mode 2. Mode 1 is when the switch is on. Mode 2 is when the switch is off. Now, there is a possibility for power converters to have a third mode. We usually do not cover that in this class, which is called the discontinuous conduction mode. So again, another assumption, let me write it down here, is we are analyzing the system under continuous conduction mode. We are going to see later what continuous conduction mode is, but the abbreviation is CCM, or if you look at the current of the inductor, it is always positive. It never touches the zero level, basically. So that means IL min is not zero, is larger than zero, okay? So that is a CCM basically requirement. So in opposed to that, let me just write it in red. So we have also a discontinuous conduction mode, which is called or abbreviated as DCM, and that is when the inductor current is actually touches or is staying at the zero level, something like this. Oops. Control Z, does it? No. So as you can see here, in the DCM operating conditions, the inductor current starts from zero and ramps up, then ramps down back to zero, and then stays at zero for a little bit of time. Like here, it is staying here at zero. So this means it's discontinuous. So that's why the word discontinuous conduction mode comes in. We pretty much try to avoid that for the most of this class. So we don't really use DCM until we get to the power factor correction, schemes. All right, so let me switch back to black. All right, so that was another assumption. Okay, so let's look at the converter under mode 1. Okay, so in mode 1, we are turning the switch on. And if you look at the diode is reverse biased by the input source. So the diode is off, so don't worry about the diode. Diode is off. And what we care about is this voltage drop. So if you write a KVL around the outer loop, VL is basically V in minus V out. All right, so this is all we need for now. And then for the second mode, we turn the switch off and the diode turns on, and I'm going to explain why. All right, so the reason that the diode turns on as soon as we turn the switch off is because of the inductor. Remember from circuit 1, inductor current is a continuous signal. It cannot jump from one number to the other, one value to the other, because it represents the amount of energy that is stored in the inductor. Because energy is conserved, therefore the inductor current is continuous. So if I open up this path of conduction, if I open it up, this current that was flowing in the inductor before has to flow through somewhere, and it pushes the diode to turn on basically. All right, so because this path is blocked, now it is actually flowing in this direction, and therefore we are basically walking into the second mode, that the diode is off, the switch is off, but the diode is basically on. Let's erase this. All right, so and that's a classic thing in all power electronic converters. When we turn the switch off, the diode is on basically. You can always argue that it happens. So again, let's take a look at this voltage drop. So now if you look at the loop on the right hand side, VL is the negative of V out. All right. So in one mode, we are applying some voltage across the inductor. In the second mode, we are applying some other voltage across the inductor. And later on, we are going to see that one of these numbers or signals is positive, the other one is negative, and on average, it should be 0. So steady state. All right, so on average, if you make sure that the voltage drop across the inductor or the voltage that is applied across the inductor is 0, that satisfies the steady state requirements of keeping the inductor current at a constant level. So, so if I draw this inductor voltage, it looks like this basically. For instance, something like this. This is T. This is duty cycle times period. This level is Vn minus V out. And this level is negative V out. All right. So either graphically, if you envision this, or you just write the equations, you say, okay, the average value of the signal is 0. So, and remember, this is happening between 0 and dt. And this is happening between duty cycle times period all the way to the end of the period. So if you just write the equation, meaning that multiply this by its time duration, and then add it with this multiplied by its time duration, it should actually add up to 0. So this is coming to write that Vn minus V out times the duration, which is dt, plus negative V out times t minus dt should be 0. This would be as if I say this area plus this area should be 0, something like that. And this leads to this expression of that you have seen before, which is the voltage transfer ratio of this converter. So V out over V in is D. Remember, D was between 0 and 1. Therefore, V out is between 0 and Vn. So that is why it is called a step-down converter, because your output voltage is always smaller than the input voltage. Now that we have this piece of information, we can go back and say, oh, wait a minute. If Vin is larger than V out, therefore Vin minus V out is positive here. I didn't know at the beginning. I just took a guess that it is positive, but now you can argue that, yes, it is positive. And since V out is a positive quantity, positive signal, then negative V out is negative, basically. So remember, always double check when you're analyzing a converter that you haven't seen before. VL, the voltage that is applied across the terminals of your inductor, in one mode it should be positive. In the other mode it should be negative. This is a general rule for all power electronic converters. Okay, so this is the voltage transfer ratio. Some people call this a DC transformer because it is like a transformer with a turns ratio of 1 to D, and it is actually converting one form of DC signal to another one. So the laptop example that we were talking about earlier, that the battery of the laptop is like, for instance, 20 volts, but the CPU consumes, for instance, 3 volts. So probably there is at least one or several stages of buck converter in that laptop, basically converter. Also in your phone, a smartphone or any kind of phone that you have, it's the same story, because the USB power is not exactly the chip power. So again, there is a bunch of high frequency buck converters in a smartphone. There's like 4 or 5 of them. All right, so this is to find the voltage transfer ratio of your topology. So please see what we did. We just analyzed or looked at the converter during these two modes, and then we looked at the voltage drop across the inductor in each one of these modes, and then made sure that on average the voltage drop on the inductor, or the voltage that is applied to the inductor, is 0. Now, there are some design equations for this converter, and there are a bunch of waveforms that I'm just going to draw it, because assuming that this is an advanced power electronics class, you have seen this before. I don't want to spend a lot of time on them. For instance, if you are curious about the voltage waveform, the current waveform of the inductor. So it looks like this. So when in the first mode, when the switch is on, or we are applying a positive voltage to the inductor, the current of the inductor is rising. And because that voltage is constant, which was Vin minus V out, Vin is constant, V out is relatively constant. Therefore, Vin minus V out is constant. Therefore, this current is actually ramping up like a linear line, basically, a straight line. In the second mode, we are applying a negative voltage to the inductor. That means the current of the inductor is, coming down, following a straight path, because that voltage is constant of negative V out. So in the first mode, the inductor is being energized. In the second mode, the inductor is being de-energized. In the first mode, the inductor is being energized by the source. So we're getting energy from the source and storing it in the inductor. In the second mode, we are releasing that energy to the output capacitor and ultimately the load, basically. So inductor is like this buffer of energy from the source to the load, basically. Get the energy, then send it to the load. Then get the energy and send it to the load. And on average, you can see that the initial value of the inductor current, which is this number, this point over here, let's call it I min, is the same as the final value of the inductor current, which is again I min. So the indication is we are actually operating under steady state conditions, and we call this I max. And again, going to a classic power electronic class or notes or a book, you can write a bunch of equations. For instance, I max minus I min which is the changes in the current of the inductor in one mode, we call it also delta IL, would be all right, so remember, changes in the current is in the current of an inductor is the voltage of the inductor divided by the value of the inductor times the time duration, assuming that this voltage is constant. It is also, this is, if I write it using the the first mode, if I look at the voltage of the inductor in the second mode, it would be V out over L times 1 minus D times T. So there are two ways of looking at the changes in the current of the inductor. Another observation that you may have is again, because we are under steady state conditions, this current, which is the current of the capacitor, on average, it is 0. So remember, steady state conditions, let me just expand what I wrote earlier. So steady state condition says that inductor current on average is a constant current, or, let me expand it here. The voltage that is applied to the inductor on average should be 0. Also, steady state, mandates that the capacitor voltage is a constant signal, or the capacitor current on average is 0. Well, you only need to talk about two of these, so the other two are the conclusion from the other two. So just keep all this in mind. So please remember that IC on average is 0. So let me redraw this down here. If I focus on the right-hand side of the topology, this is the current of the inductor. Then it is feeding a capacitor which is placed in parallel with a resistor. All right, so this is IC. IR. So remember, KCL tells us that IL is always equal to IC plus IR. But looking at the average values, okay, the average value of the current of the capacitor is 0, so forget about it. And IR is nothing but V out over R. So on average, this current and this current are the same on average, not on the instantaneous value. On average, these two are the same. So I can write okay, how did I get the right-hand side over here? I just looked at the triangular waveform of the inductor current and wrote the average value of the signal. If I have a symmetric triangular waveform, the average value of that waveform, which is, for instance, this dotted line, it is just the average value between Imax and Imin, basically. So average value of the inductor current is Imax plus Imin over 2. At the same time, it is the same as V out over R. So this is how you can actually proceed to finding Imax plus Imin, because on one side, you have the difference between Imax and Imin, and on the other side, you have what happens if you add Imax and Imin together. It would be 2 times V out over R. So if you solve these two equations, you will end up with an expression for Imax and Imin. All right, I have the expression here. Let me just write it over Or I can just write it like this, IR, or let's say, yeah, IR plus half of delta IL. This would be IR minus half of delta IL. And remember, IR is V out over R plus delta IL. We had an expression up here or here, whichever you want to use. A lot of times you use it in a way that only V out appears in the equations, not V in. So I'm just going to write it that way. So it's going to be 1/2 of all right, so this is I max, and I min is almost the same thing with a negative sign over here. All right, so something like this. So remember, if you don't want to see V out, you can replace it with V in. V out is just D times V in. So whenever you want, you can do that. So now, having I min determined, or we have an expression for I min, we got to make sure that I min is positive, because remember, one of the assumptions was that we are operating under continuous conduction mode. So we made this assumption over here that we are operating under continuous conduction mode, or the minimum value of the inductor current is positive. Now that we have an expression for that minimum value, this should be positive. So this guarantees continuous conduction mode. All right? So once you do that, you're going to realize that the inductor should be larger than this expression, 1 minus the value of the duty cycle times the value of the load divided by twice the switching frequency. Switching frequency is 1 over T. So use this equation or inequality to determine the value of the inductor, because a lot of times when the customer comes to you, you know how much power this converter is supposed to maximum, worst case scenario, maximum value of the load, or the minimum value of the power, how much it is. You know the value of the input voltage and output voltage, and even if they are in a range, you can actually see how 1 minus T is maximized, which is the minimum value of the duty cycle. And the switching frequency is usually determined by you as the designer. For instance, you pick the switching frequency to be 100 kilohertz or 150 kilohertz or 200 kilohertz, something like that. So you determine all of these numbers or calculate all of these values, and then it's okay, L should be greater than this expression. So remember, you maximize, you make sure you maximize this expression, meaning that if your R has a range, you have to use the maximum value of R to maximize this. If the duty cycle has a range, you have to use the minimum value of the duty cycle to maximize 1 minus duty cycle. And then make sure L is even larger than all of those maximum values. So this is a design equation to find the value of the inductor. For the capacitor, so the assumption that we made was, here's the assumption that the capacitor is just very large, or the voltage of the cap is almost like a DC voltage. So how are we gonna, make sure that happens? Let me switch back to black, and now let me draw the capacitor current first. Okay, this is one switching period. This is the end of the first mode, which is the duty cycle times period. Capacitor current looks like something like this. On average, it should be 0. Remember, a steady state condition mandates that on average, the capacitor current should be 0. So I'm looking at a signal that is hovering around 0 anyway, some positive areas, some negative areas, and they should cancel each other. How did I draw that waveform? The way I drew that waveform was basically I looked at this equation. Okay. The capacitor current is nothing but the inductor current minus the resistor current. And remember, the resistor current was the average value of the inductor current. So technically, in order to find the capacitor current, you look at the inductor current and then subtract its own average value from itself. In other words, I'm actually going to place, in order to draw the capacitor current, I'm just going to place my origin or axis over here. And that's actually my capacitor current. So it's just capacitor current is just the inductor current shifted down so that its average value is 0. So that's where this waveform comes from. And then let me draw also the output voltage. All right. First of all, remember the output voltage is almost a DC signal. So if you look at it on an oscilloscope and if you don't zoom in, you almost see it like a flat line. It's almost a DC signal. But if you really zoom in on the AC part, you see some sort of a ripple. Or when you do simulation, you can easily look at that ripple. For instance, in this top triangle, you can see the cap current is positive, therefore the voltage should be basically rising. And then in this bottom triangle, the cap current is negative, therefore it is basically going down, something like this. And then again, it is going up. Okay, I didn't do a good job drawing this. Let me erase this. Oh. And so it's coming down, something like this. So there is a little bit of a ripple. I didn't draw it really well. It is not actually sinusoidal. It's like a distorted sinusoidal kind of a signal. Once you do simulation, and we are going to simulate these converters later in this class anyway, so you can zoom in and actually look at the pattern of the ripple of the output voltage. So we call this delta V out. Okay. So in order to find delta V out, I can actually focus on how much the capacitor voltage rises for a positive triangle of the current, or how much it falls for a negative triangle of the current. So for instance, if I just focus on this positive triangle of the current, it should give me the difference between this point and this point. All right, so let's do that, which is delta V out, by the way. So remember, for any capacitor, the amount of, from physics classes, the amount of electric charge stored in the cap is the value of the cap times the voltage of the cap. So changes in the charge would be the cap value times changes in the voltage. We are looking for the changes in the voltage, therefore we have to find changes in the charge. And changes in the charge, remember, charge is the integration of the electric current. So if I have a waveform of the electric current, I just have to find the area under that electric current. In this particular case, the area, that red area under that triangle. So, so this would be the area of that triangle, half of the base of the triangle is half of my period times delta IL over 2. All right. So this is the period times delta IL over 8. All right. So this is delta Q, which is C times delta V. So on the end, you can actually write this equation. 1 minus D divided by all right, so this is another design equation. Guarantees that your capacitor is large enough so that your delta V out over V out, which is the ripple divided by the DC component, is basically insignificant. So you use this equation to find the right value for your cap. And please remember, if these signals have a range, for instance, if the duty cycle has a range, you have to put the minimum value of the duty cycle here to maximize 1 over D, something like that. One thing to observe in these two equations, the one that we had up here to size the inductor, as well as the one that we have down here to size the capacitor. F, which is the switching frequency, appears in the denominator of both of them, meaning that if you increase the switching frequency, then you will need a smaller inductor and a smaller capacitor, which is good. That means your converter is going to get smaller because the most of the volume and the weight of a converter comes from its inductor as well as its capacitor. So that's a good trend. If I increase the switching frequency, then I will need a smaller inductor as well as a smaller capacitor. But obviously, I cannot keep increasing the switching frequency. There's a limit to that. And there's a mechanism which is called the switching losses. We are going to see that later. And if I keep increasing the switching frequency, also the switching losses is going to increase. And that means you're losing a lot of energy in your switches, which are two things. There are two disadvantages. One, obviously, your efficiency goes down. The other one is, in order to get the heat out, you have to use a bigger heat sink. So you're trying to make your inductor and capacitor smaller. At the same time, you're making your heat sink larger, or you have to add a fan to your converter, a cooling fan. So there's a compromise involved. So just keep in mind that usually because of the limitation that we have, so technically we want to go as high as we can in terms of the switching frequency. The limitations are the switching losses here. The other one is how fast our switches are. We assume that our switches are ideal. As soon as we command them to be on, they turn on. As soon as we command them to turn off, they turn off. Obviously, in reality, that is not the case. There is a little bit of a time delay, and basically it's like the transition response or the turn on delay or turn off delay of the switch. And usually the switches that we have these days available on the market, like if you're talking about a power MOSFET, you can achieve switching frequencies of maybe 200 kilohertz, 500 kilohertz, but not, for instance, 10 megahertz. You cannot go that high. Even though your inductor and capacitor are going to get really small, you cannot really go that high. Unless you are talking about a very, very small converter, for instance, in your cell phone. Now, in a cell phone, weight and volume are very important. Efficiency is not that important, and you're not processing a lot of power. So if you lose, for instance, 2 watts of power, it's not like your phone is going to get overheated. So like in a cell phone, for instance, a smartphone, the switching frequency of those buck converters is actually relatively high, like 10 megahertz or maybe 5 megahertz. But for a classic DC-DC converter that you use in a non-portable application, your switching frequency is somewhere, and it is processing, for instance, 1 kilowatts, it is about maybe 100 kilohertz, okay? If you're using IGBTs, and we are going to introduce IGBTs later, then the switching frequency should be a little lower because IGBTs are not as fast as MOSFETs. Any questions so far? Okay, so this was a very brief review of the box topology. I'm sure you have seen it before. Before we move on to the next topology, let me just write a bunch of other equations for the sake of being complete. All right, where did it go? Okay. So remember, we assume that all of the components are ideal. Therefore, the efficiency of our converter is 100%. So just bear in mind, you can sometimes use this to transfer the signals from the output side to the input side or vice versa. So we are looking at an ideal converter. That means there is no losses. Okay? Or 100% efficiency, or input power is the same as the output power. Now, as long as the input power is concerned, we are looking at a DC source. So the power of a DC source is the voltage of that DC source times the average value of the current. On the output side, we are looking at a basically resistor, which is V out times all right, something like this. All right. So if I rewrite this equation, I can actually get this. All right, so we already knew that V out over V in is D. Now the new conclusion is the average value of the input current over the average value of the output current, which is IR. That is also D. It's like, again, DC transformer, and the turns ratio is D. So your voltage is being a step down, your current is being actually a step up. In terms of some waveforms, let me just draw some of the other waveforms. So that you guys have seen at least one. So if you want to draw, for instance, the input current. Now in the Bach topology, the input current, or the current that is drawn from the source, is the same as the current that passes through the switch. So if you look at the schematic of the converter, this is your input current. And this is the switch current. All right, they are basically the same. And in order to draw that, you just have to look at mode 1, because in the first mode, the switch was on and the inductor current was passing through the switch. So if you look at mode 1, this is the current of the switch, which is the same as the current of the inductor. In the second mode, the switch was off. Ideal switch, zero current. So if you are trying to draw the input current, it would be the same as the inductor current in the first mode, and then zero in the second mode. All right, something like this. So this is your input current. One of the disadvantages associated with this converter is that the input current is discontinuous. Sometimes you are drawing power from your source, and sometimes your source is kind of disconnected from your topology. So you are not continuously drawing power from the source. So that's the disadvantage of this converter. And this discontinuity may cause some EMI issues on the source side, some ripple on the source and stuff. Other loads, if we have other loads connected to the source, they are going to see some noise and something like that. Now, in the end, if you are interested in drawing the current waveform of the diode, please remember this for your homework assignments and quizzes. We always define the current of a diode flowing from anode to cathode, and the diode current should always be positive. or 0. You can never have negative current for the diode. All right? So, I mean, assuming that you are following the right direction. So in order to find the diode current, look at mode 1. In mode 1, we said that the diode is off, so no current. In the second mode, the diode current and the inductor current are the same. This is ID, which is the same as IL. All right. So to draw the diode current, all I have to do is follow the inductor current in the second mode. In the first mode, it is 0. And then here, it does something like this. Now, why do we care about these signals? Because sometimes if you are interested in finding the losses, for instance, in your switch, which is the same as the input current, and if your switch is a MOSFET, you have to look at the RMS value of the input current. So you have to know what it looks like and then go ahead and find its RMS value. For the diode, sometimes you're interested again for the losses and you're looking for the average value of the diode current, which is the average value of this trapezoid. So basically you have to know what it looks like and then go ahead and find its waveform and find its average value. And obviously if I apply KCL to this node, for any instant of time I can say the switch current plus the diode current is the inductor current, right? So just keep that in mind. If you want to verify your solution in the end, the switch current at any given time plus the diode current should be the inductor current. And these are non-overlapping signals, by the way, okay? So I somehow, I don't know why, but this is a little bit wider, but they are supposed to be on the same time scale. All right, I don't know why it got wider a little bit. Any questions? Okay, I think I'm gonna stop here now, and then next time what we are gonna do is we are gonna look at the boost topology. Do we have any questions? So please do not leave the class because I want to mention something about the power electronics lab. All right, so I'm just going to stop the lecture now.